Hello students, welcome to my channel Arun's Physics Portal. In this lecture, I will discuss about the Butterworth second order high pass filter. This topic is useful for MSc Physics and Electronics students and also for BE and BTech students of EEE and EC branches. The JRF and NET aspirants will also find this topic useful. The complete note of the topic is given here for your convenience. I hope you enjoy going through it. Now let us come to the topic. Figure 1 shows you the Butterworth second order high pass filter. The circuit enclosed within this curve is your non-inverting amplifier, where RF is the feedback resistor and R dash is the resistor connected between the ground and the inverting input of the op-amp. The circuit within the pink curve, pink enclosure, is your first order high pass filter. Okay, so we have here only one resistor and a capacitor in first order high pass filter. If you add one more RC network to this one, we get your second order high pass filter. So in this case, we have two capacitors and two resistors. Okay, this junction is termed as A node, this is B node, and this is C node. If this is the current I1 supplied by the input potential Vi, then a part of it is flowing through R1. So this is I2 and the rest I3 flows through C2 and R2. Okay, we have shown you the distribution of current in the circuit. Using the voltage tracking property of the op-amp. What is the tracking property? Tracking property is that the potential at the two inputs tends to track each other. So if this is plus and this is minus, and if the potential here is V1 and potential here is V2, then V1 and V2 tends to be equal to each other. This is the voltage tracking property of the op-amp. So, using the voltage tracking property of the op-amp and applying voltage divider rule, we get VB and VC will be equal because of the voltage tracking property. And what is VC? VC is simply equal to R dash upon R dash plus RF into V naught. So we have V naught is 1 plus RF upon R dash into VB, and this is AF into VB, where AF is 1 plus RF upon R dash. This is the gain of the non-inverting op-amp. So we are applying the voltage divider rule at the point B. So we get VB equal to R2 upon R2 plus 1 upon SC2 into VA, and we get VA in terms of VB. Okay. Now again apply KCL, Kirchhoff's current law, at the point A. So we have I1 equal to I2 plus I3. I1 is V1 minus VA upon 1 upon SC1. This is equal to I2. I2 is equal to VA minus V0 upon R1. And I3 is VA minus VB upon 1 upon SC2. If you solve this, we get this equation. You simply go on putting the value here. Okay. So insert the value of VA from equation 2. What is equation 2? I have written here. I have copied it here. What is equation 2? To put the value of VA in equation 3 from equation 2. So this is what you get. This is simply mathematical calculation. So this, even though this is a lengthy one, I have done it for your convenience. So we have now only one variable here, VB, because we have converted VA in terms of VB. So we get VB in terms of simply V0 and VI. So this is your equation 4. This is a long term and we have replaced it by a variable Y. So where Y is equal to this one, and we are solving it to get a simple value of Y equal to this. Okay. So this is simply mathematical calculation, nothing else. Now for the non-inverting op-amp, we have output V naught equal to AF into VB. Okay, so this is AF. What is the value of VB? Put it from equation 4. I have copied the value of VB here. So put the value of VB here using equation 4 and go on solving it. This gives you this value. Bring all the terms containing V naught on one side and Vi on the other. So we have this equation. The equation is a long one and the process is lengthy. I have done it for your convenience. So this comes out to be AF into Vi S square R1 C1 R2 C2 using equation 5. What is 5 equation? This is I have copied here. So now find the value of V naught upon Vi. So if you get the value of V naught upon Vi, this comes out to be this. Okay. So in the denominator, we have a term containing S square, a term containing S, and a constant term. Now, the standard transfer function of the second order Butterworth filter is given by this. AF into S square upon S square plus S alpha omega n plus omega n square. So compare equations 7 and 8. In both the equations, we have a term containing S square. Okay, we have a term containing S. So this is your second term containing S. And then we have a constant term, this. So omega n square must be equal to 1 upon R1 C1 R2 C2. Okay, so if you compare equation 7 and 8, you find that omega n is 1 upon root over R1 R2 C1 C2. And this is your equal to omega L, and this is nothing but your lower cutoff frequency. And the coefficient of S in 7 and 8 have been equated here. So alpha omega n is equal to R1 C1 plus R1 C2 plus R2 C2 into 1 minus AF upon R1 C1 R2 C2. Okay, now we assume for simplification purpose that R1 and R2 are equal, each being equal to R. C1 and C2 are equal, each being equal to C, and therefore omega n will be equal to 1 upon RC. Okay, so R into R gives you R square, C into C gives you C square, root over this is gives you simply omega n equal to 1 upon RC. And alpha omega n is 2RC plus RC into 1 minus AF upon R square C square. So RC cancels out. So this is equal to 3 minus AF upon RC. Okay. So alpha omega n is equal to 1 upon RC. So this 1 upon RC cancels with this omega n. Isn't it? This omega n cancels with 1 upon RC here. So alpha is simply equal to 3 minus AF as omega n is equal to 1 upon RC. For Butterworth second order high pass filter, we have alpha equal to root over 2. So the preceding equation gives you root over 2, alpha is root over 2 is 3 minus AF. So root 2 is 1.414 is 3 minus AF, or AF is equal to 3 minus 1.414. So this is equal to 1.586. Or put the value of AF here, 1 plus RF upon R dash is 1.586. So RF upon R dash is 1.586 minus 1. So this is 0.586. So now we get a relationship between RF and R dash for getting Butterworth's second order high pass filter. So RF is equal to 0.586 R dash. This equation 11 can be used to get maximally flat frequency response of Butterworth's second order high pass filter. Using equation 7, the magnitude of the gain can be found as follows. So we are making use of a standard transfer function for the Butterworth second order transfer function, and we write therefore V naught upon Vi is AF into S square upon S square plus S alpha omega L plus omega L square. So divide both the numerator and denominator by S square. So this gives you AF upon 1 plus S upon S square alpha omega L plus omega L upon S whole square, or this is equal to AF upon 1 plus 1 upon S alpha omega L plus omega L upon S whole square. Okay, this is simple mathematics. So this is equal to AF upon 1 plus alpha omega L. S is equal to j omega, so we write here j omega. This is omega L upon j omega whole square. So this is equal to AF upon 1 minus j, because j square is minus 1. Okay, we have 1 upon j. So this can be written as minus j square upon j, isn't it? So this is minus j. So we write here minus j. So this is minus j alpha Fl upon F minus Fl upon F whole square. So V naught upon Vi comes out to be AF upon 1 minus Fl upon F whole square minus j into alpha Fl upon F. Okay. So magnitude of V naught upon Vi is AV is AF upon 1 root over 1 minus Fl upon F whole square to the whole square plus root over 2 Fl upon F whole square, where alpha is equal to root over 2. Okay, this comes from the fact that if we have an equation x equal to a plus jb, then mod of x is equal to root over a square plus b square. Keep in mind. So AV equal to AF upon, this is your a minus b whole square. So this is 1a square plus b square minus 2ab plus 2 times FL upon F whole square. So this minus 2 FL upon F whole square and plus 2 FL upon F whole square, they cancel out. So this cancels out with this one, and we have AV equal to AF upon 1 plus FL upon F to the power 4. In general, AV is equal to AF upon 1 plus FL upon F to the power 2n. For first order high pass filter, n equal to 1. For the second order high pass filter, n equal to 2. And for the third order high pass filter, n equal to 3, and so on. But as we go to higher order filters above the second, not only does the analysis becomes more complex, but the system also becomes unstable. Hence, to maintain the stability of the circuit, we mostly confine ourselves only up to second order filters. आपने देखा है कि सेकंड ऑर्डर फिल्टर में ही कैलकुलेशन बहुत लेंदी हो गया है. So if you go for higher order filters, it will become more and more complex, and system will also become unstable. So following conclusions may be drawn from equation 12. At f equal to 0, Fl upon F is infinite, which gives you AV equal to 0. As F increases, Fl upon F decreases, and so AV increases. At F equal to Fl, AV equal to AF upon root over 2, and as F tends to infinity, AV tends to AF. I have never written that F equal to infinity, so AV equal to AF, because F will never become infinite. It will tend towards infinity and will never become infinite. Clear? So, the frequency response curve of the Butterworth second order high pass filter is shown in figure 2. On the x-axis we have frequency, on the y-axis we have gain. So AF is the maximum gain. We have shown it by a dotted horizontal line. As frequency increases, the gain also increases. At frequency FL, gain becomes AF upon root over 2, as we have shown you mathematically. As it goes to infinity, frequency tends towards infinity, the gain approaches AF. So note that in exam or anywhere, do not show that this curve is touching this line AF anywhere, or it is intersecting this line, because they will meet each other only at infinity. So we can say that the curve meets the dotted line asymptotically. The slope of this curve is 40 decibel per decade. That means when the frequency increases by 10 times, the gain increases by 40 decibel. So even though the mathematical calculation is a bit lengthy, I have done it for your convenience. So this is all about the Butterworth second order high pass filter. So I have shown you how Butterworth's second order high pass filter can be designed, and to find out its cutoff frequency and the gain equation. Though the equations are somewhat lengthy, I have solved them for your convenience. I assume you like this presentation. यदि आपको मेरा प्रेजेंटेशन अच्छा लगा हो तो इसे लाइक करें, शेयर करें और मेरे चैनल को सब्सक्राइब करें. So thank you for watching. See you next time with some other topic of interest. Till then, goodbye.